Buggy's come to many of these conferences, and he always gives an interesting perspective. He almost had to cancel, but he flew up this morning, and as soon as he's finished, he'll be flying back.
This presentation consists of is an entirely different approach to converting thorium into uranium-233, and the approach is based on our many years' experience in colliding beams of nuclei. The process is here schematically presented as thorium being converted into protactinium, and this process, the cross-section for neutron interaction with thorium at thermal temperatures is 1,000 barns, and this therefore it is believed that this is the only way to produce it, to work at thermonuclear temperature of the reactor. But on the other hand, say 2 MeV neutron with thorium has cross-section of 2 barns, not 3,000 barns, yet has the same reactivity. Namely, very often people mix up cross-section with reactivity. Figure of merit is not cross-section, but cross-section times velocity. And thermal energies velocities are 1,000 times lower, and therefore the product of sigma and velocity at thermal energies is the same as the one at 2 MeV. 2 MeV cross-section is 2 barns, but million times higher velocity. Therefore, first thing I'm saying here that there is no reason to do this in a reactor at thermal neutrons. What we want here is something like that. We have now, if I have convinced you that 2 MeV neutron will do just the same job as thermal neutron here, then we can think now of a thorium nucleus, and let's think now of having a pulse of 100 neutrons going against it. And this bunch is exactly of the same diameter as the nucleus of thorium. Is this an impossible picture? It is completely possible and doable. How? If you have a colliding beam of thorium colliding with one thorium nucleus colliding head-on with another thorium nucleus, at each having energies of 200 MeV, which would come roughly 1 MeV per neutron, then essentially the left-hand side, you can say, left-hand side thorium nucleus sees the right-hand side as 141 neutrons coming against it, and the other way around too. So essentially, by doing it this way, instead of 1 neutron interacting, we have 142 neutrons interacting, which is the neutron content in thorium. This results in something that a virtual state which will have a Z180 and 464 mass. What does it exactly look like? Nobody knows, but the impact will be enormous. But what is going to happen here? There's going to be tremendous exchange between neutrons and protons, and certainly probability with 100 neutrons and 90 protons that exchange like this can happen. That is, that 2 protons go in and 1 out. It produces immediately uranium. It should be very likely, particularly in view of this now enormous cross-section. We have said now the cross-section, the reactivity is equal to that one of thermal neutrons times 100 or 160 times more. So we expect 160 barns cross-section for collision of this type. So if this takes place, there will be then all the creation of 233. Here some will be left, say, radium-88 and 2 neutrons, and these 2 neutrons will cause fission of uranium-233, all in one shot. So you imagine now that we have 2 accelerators, 200 MeV, shooting against each other. First of all, that's each accelerator would be 100 meter long, approximately 30 kilovolt per centimeter, 100 meter long, if charge Z is 1. But the recent experiments at Brookhaven have shown that uranium can be stripped completely of all electrons with a Z90. So with the Z90, or in this case with Z90 here, 2.2 million volt accelerator will produce 200 MeV beam. So I don't need 2 accelerators 100 meters long. One accelerator 6 feet long will do the job. If the stripping has taken place, and it has taken place at Brookhaven colliding beam system, which has also accelerated completely stripped uranium nuclei and collided them, and has observed a cross-section of uranium-uranium interaction at extremely high energies of 480 barns. 480 barns cross-section, but about 90%, well, a great fraction of it is due to some relativistic effects. Nevertheless, we can reasonably expect for this process a cross-section of 100 barns. 2 MeV. Now, how is this going to be accomplished? Let's look now at the history of colliding beams. Colliding beams of nuclei, in this case protons, first time were made in Geneva at CERN in 1972. You can see here there are 2 rings where neutrons were stored, and you see they intersect at 135 degrees here, so it is almost head-on. So this is the colliding region. First observation is that in colliding beams, unlike in plasmas, the confinement time is very large. In the first colliding beam, it was 2 months. They would inject, store the proton beam, and it will drop to 1/E in 2 months. Of course, they didn't wait for this. They didn't want to drop it more than few percent, but it is remarkable. And the reason, as opposed to plasma, it's an ordered system. Plasma is random motions. It's ordered systems where external signals can constantly stabilize a system where there could be feedback. And as I say, they were able to really have this type of times. And I believe at much larger machine, at Thorium Lab and so on, you can take sometimes 6 months. But of course, nobody waits its intensity to drop down because the collision rate drops down. That was there. Here, this is the cross-section that was measured at Brookhaven, uranium. And this is the only information that exists in the world about uranium collisions. So we are applying this now to thorium collisions. Okay, so now we see here 2 beams in 2 rings are intersecting, but we are more clever than that. We have made a machine where we have made 1 beam come around and collides head-on with itself. Beam collides with itself head-on. But before I get to that, I told you that at Brookhaven they have succeeded in fully stripped uranium, and it was not a small job. It has 3 stages of pre-analysis, pre-preparations, and electron beams. So you can see here. Let me see like this. See, this is the prep system. This is an RFQ. There is a LINAC, and only here now the beam was completely stripped of all electrons and then enters the storage link. it is a significant equipment. Nevertheless, it works. It makes it possible to have an accelerator that would be 100 meter long, 3 meter long. 30 years ago, I have, together with BASIC of Los Alamos, devised a system which is called self-collider, where beam collides with itself. We call it auto-collider, which we built 4 models, and I'm showing you the model number 4. The one beam, here is an accelerator, 1.5 MeV accelerator, injects D2 plus beam. It is a molecular beam of deuterium, which enters the center of this system, gets dissociated, and creates an organized plasma, which we call MIGMA. These are pair of superconducting magnets, 3 Tesla midplane, and the vacuum has to be perfect, like at CERN. Vacuum has to be 10 to the minus 11, in operating condition 10 to the minus 9, because of what? Because the enemy of beams is the process called charge transfer. Charge transfer process consists of ion colliding with the gas, picks up an electron, ion gets neutralized, and beam, it's a runaway beam, it's a runaway plasma. Therefore, vacuum has to be nearly perfect, and took years at CERN to make it this way, to succeed in doing that. Here is another description of the process. So D2, we have introduced D2, the beam gets dissociated, the undissociated part goes to the beam dump, and dissociated is trapped because suddenly its momentum is 1/2. E/m ratio goes to half, and therefore, because all dissociation took place for the reasons that we'll explain maybe later, in the center. So here in the center, we can see it's like an infinite number of beams colliding each against each other continuously. Here is a better picture of this. Okay, the molecular beam comes here, gets associated, the associated beam is captured here, and this is now undissociated part, which at that time was majority, but actually we have a scheme where the undissociated part will be accelerated and done the same, and again accelerated and accelerated, which we call exciter. Here is essentially the real picture, the engineering picture of the device. The D2 beam was entering here. All the MIGMA is created here. Looking from top, this is the MIGMA, and fusion products are channeled through magnetic channel left and right. Fusion products therefore can be collected or decelerated to get energy out of them. So convenient for direct conversion of fusion energy into electricity. And what we have established, as you know, in all fusion systems, there has never been longer confinement time than a fraction of a second. We have accomplished 24-second confinement time. First, we fill the machine and then stop filling, and you can see that the decay is showing even longer confinement time. Actually, if the vacuum were better, it would be 100 seconds. This we have patented as a process, but basically, and published in a number of PhysRev letter papers, that we have exceeded space charge limit. Space charge limit, when repulsion between ions destroys the beam, we were able to do that because actually we have made electrons oscillate to stored ions, and through various tricks established a stability using the nonlinear stabilization. None of this is possible with plasmas. It has to be ordered synchronous system which can exchange signals and feedbacks. So in that experiment that was done 20 years ago, we have produced the reaction was DD, or should be here, D plus D going into triton and proton. And when D collides with the gas, there is always gas or the target, non-moving target, stationary target will be DD reaction. But if they are moving against each other, the energy is 1 MeV higher. So here is the peak that shows that it's produced in beam-beam collisions, and that we have produced an awful lot of tritium. So much so that the Department of Energy didn't like this project to continue. You know what tritium is used for. It was, it appears to have been unacceptable to them to have a small company manufacturing tritium in the middle of town. What is important in this process is the MIGMA process takes place here. The products are magnetically funneled, and at that time the idea was to put a decelerator, put it at positive voltage, so that this beam will now feed electric energy into the grid, so for direct conversion. However, for the production of thorium, of uranium-233, there is no need for that. We could simply magnetically analyze it and store it in a bucket. But basically, the process is all taking place in vacuum. There is no interaction. There is no other media than a gas. This was a 1 meter diameter cell, and the volume actually was only of the reactor interactive volume was 5 liters. And we have produced energy so that we could extrapolate. So we envision a fission or fusion, and next week I will announce fission reactor consisting of cells 1 meter in diameter, producing essentially 1 megawatt that could be stacked, and that taking advantage of economy of mass production. It will be extremely cheap. Or this is other ideas of stacking. Here we already have 3 of those cells in one. That system was focused in the jargon of accelerator physicists as weak focusing system. Okay. Since that time, strong focusing was invented. And strong focusing system, I will not explain you here because it's complicated. Strong focusing system can store 100 times more intense beams. So that was a revolution in the science of accelerators, the invention of strong focusing. And strong focusing consists of alternate focusing, defocusing forces. But anyhow, we had a design by one of the inventors of strong focusing, designed for our next model, which was never built. So I will. The best system would be to have absolute maximum confinement, is that whenever non-interacting go out, they are returned. So essentially to have about 6 accelerators pumping out and increasing density. What we predict here now, with some reasonable assumptions, but first let me tell you, first difference that I should have mentioned to you between beam on target and beam-beam. Beam on target, reaction rate is proportional to the ion current. Beam-beam is proportional to the square of ion current, because each ion sees another ion, and so this is an enormous difference. You have square. Second thing is beam on target is a single passage, while beam-beam collisions, the passage that is determined by the rotational frequency, essentially million passages per second rather than a single passage. So there is no comparison between a colliding beam system and beam on target system for production of uranium or anything. So to make a long story short, we predicted with a production rate of about 10 to the 18 to 10 to the 19 atoms per second, or about 10 to 1,000 grams a day. And this is shown here. I can send you this. So, thank you.
Right on time, Doctor. 1 second.